And Gauss's law will be taken E dot dA, and A is in the same direction as E. And so the dot product goes, and the energy is scalar, the electric potential is scalar. So we're dealing now with scalars, which is much better. It's ready, right?
I think so.
I'm handsome there as well. The camera of the Zoom is it's not good.
Yeah, if you want to put it first.
Yeah, I'll have it here. Oh, used to be maybe up because of the lights. Oh, yeah, that's very good. That's very good. Mhm. That way. Let's see if I write something.
Is that your name?
No, that's hello. Nerd. Okay. Marhaba. Okay, so again, we will be talking about the flux. The flux will be scalar because it's E dot dA. And we'll be using Gauss's law. E dot dA, we will use Gaussian surfaces where E and A are in the same direction, so the dot product goes away. And then the energy and the electrical potential. So everything is going to be a scalar, which is easier than uh, before. No one's on Zoom. That's good. Okay. Okay, let's talk about the flux. So the electric flux, we express the electric flux like it's about how much of the electric field goes through a surface. That's the meaning of it. They tell you sometimes the number of lines, but we said that if you have a charge, if you remember, the electric field lines around it look like that, and the more lines, the more the electric field. So we have more electric field around it if it has more lines or stronger electric field. So if you have a surface and there is an electric field, let's say in that direction, the more lines, the more electric field. So the number of lines or how much electric field, this is the same sentence with like one coin with two faces. That's it. So how much electric field is going through a surface? I don't believe in other word how many lines because number of lines all the time is infinite. There is an electric field at every single point, so you have infinite number of lines. But on the board or on the textbooks, we use number of lines just to show you that the electric field is stronger. That's what we mean. Anyways, if you look at this electric field as in my summary, then this electric field, let's take one of these lines, it has two components, one tangential to the area and another one perpendicular to it. This one is really the one that goes through the area, and that one doesn't. It's just tangential to it. And so I care about the number of lines going that way, or the electric field that is going that way through the area. So we say that the electric flux, and that's the sign for it, it's phi or phi, a capital letter. The electric, there is a magnetic which is B in there, is equal to E, which is going that way, that component multiplied by the area. But that component is the electric field itself by cosine this angle, which is theta. That's E. E cosine theta is that component. So E, that's the electric field. Let's say this is the total electric field by cosine theta. This is that component that goes through the area. So EA cosine theta is the electric field that goes through the area multiplied by that area. The bigger the area, the more electric field that goes through. Let's say I take only this area, some electric field will go through. If I take this, electric field will go from here and there and there. The higher the area, the higher the electric flux. And depends on the angle because I need that component. And the higher the electric field, the higher the flux. Because it's how much electric field goes through an area. So the flux should depend on cosine theta, E, and A linearly, and that's the equation for it. And because something by another thing by cosine, the angle between them is the dot product. So this is actually E dot A. But what is the direction of A to say that? This is cosine theta between the direction of the electric field and the normal to the surface. So let's define that the direction of a surface is the perpendicular line on it, perpendicular arrow on it. So if you define that, this is going to be the angle between A and E. And then we can write it in terms of the dot product, which is E dot A. Yes?
I can't remember. Is there a convention for if it's positive or negative?
Okay, so the direction of the area, in this case, if it's a sheet, the direction of it is perpendicular to it, but it has two directions. It could be in that direction, it could be in that direction. It's a matter of convention. But when we talk about flux of the electric field, we will take this direction actually, which is close to the electric field, which makes an angle less than 90 degrees with the field. If the field is in that direction, I will take that one. But if it's a closed area or curved area, let's say it's an area which is curved, it's outwards. Even if it is that way, let's say that's the cross section of an area, this is outwards, and this one, I know it's curved to the inside, but it's a part of this closed area, and so it's outwards. If it's only part like that, like by itself, just that curve, it's outwards in that direction, which is down. But if it's a closed area, and every point on that area, closed area, every point on it should be to the outwards. That's the direction of the area. If it's not closed, only curved, it should be outwards in that way. If it's a sheet, it can be in that direction or that direction. We take the one that makes an angle of between 0 and 90 degrees with the electric field. Is that clear? And so we take, and so if you want to find the value of the flux, maybe the electric field here is different from the value of it in here. And maybe here is also different. Maybe the direction is different. So to find the total flux through some area, you need to take an integration. E at any single point dot dA at that point. And you make an integration. You sum over all of those ones. D dot dA here plus E dot dA here plus there and so on. And you make the integration. That will give you the total flux through your area. If your area is closed, it's a closed area, you add a circle, and that's it. Yeah.
So what is really the difference there when you're saying E dot A versus the integral of E dot dA? Like, what is the difference between those?
Okay, the difference is that in this case, E is the same everywhere and has the same direction. So theta is the same everywhere. E makes the same angle with A. A has the same direction everywhere because it's a sheet. It has the same direction. And E is the same magnitude and the same direction everywhere. So the angle is the same and E is constant. A is just the whole area and it's E dot A and that's it. But if E is different from point to point, the magnitude is different or the direction or both, then you need to take the flux through one of the areas plus through another area plus through another area and so on because the cosine theta can be different. E can be different. So you need to have E inside the integration and integrate. E will be different from point to point. dA cosine theta. So cosine theta is going to be different. E is going to be different from point to point. So you take all the points and sum all overall of them. Why I took a lot? I took a lot.
It's your TA.
Okay. Chat A.
TA talk a lot.
That's a good one. Okay. So that's it. And for a closed area, we have this sign. What I'm going to say now, I'm trying to say it in a minute. What I'm going to say now is not required, okay? Is not required. So if you have charges inside a closed area, like some charges Q1 and Q2 and Q3, point charges or even distribution of charges, the electric field flux through that area is that one. Integration over the closed area. You want to integrate over dq inside the area. For every dq integrate over all of them. 4 pi epsilon naught r squared, and it's going to be in r hat. That's E due to every little point charge. Dot the area. The area is dA. That's it. This one is called the solid angle. Like, you know the normal angle, which is this arc divided by r is equal to this angle. But if you are talking about space, like a cone, let's say this is a cone, for example, this area divided by r squared is going to give you the solid angle. That's called the solid angle because it's a space angle. It's not only in a plane. So that's the definition for it. The area divided by the area in dot the direction of r hat divided by r squared. So this is the solid angle, which is d omega, we call it. You can take everything out. You have dq and d omega, but d omega for a closed surface is going to give you, there's an integration for this. That's dq. There's an integration for dq's as well. So the integration for the area is going to give you 4 pi. The solid angle is going to give you 4 pi. How to know that, I'm going to tell you. And the integration for this is going to give you just the value of the q inside. How to know that? Let's take this solid angle, r hat dot dA over r squared. Let's take a simple example, which is a sphere, which is a closed surface. Take any closed surface, but the sphere is the easy one. Exactly like here, you take the circle as the easy one. I can't say, and the r changes. But if you go around, it's 2 pi. It doesn't matter what the curve is. The same as if you go around and take the whole space, a closed space, it doesn't matter if it's a sphere or not. So if you take a sphere, r hat is in the same direction as the area because it's a sphere. It's r hat and area on the same direction. So the dot product goes, and this dot that, this is 1. This is going to be dA over r squared. R is constant for the sphere. You take it out, and the area is 4 pi r squared. This cancels, and the solid angle for the full solid angle is 4 pi. It is not required again. So that's why it's 4 pi, and it cancels with 4 pi, and you're at the end left with the integration over dq inside. So that's why the integration over the flux over a closed surface is q enclosed over epsilon naught, which is Gauss's law. That's why, but it's not required from you to derive it. Okay. What about the charges that are outside? Anyone here, this will give a flux through this area, and through another, this will give a flux through here and there and there and so on. But the flux through this area, which is in that direction, and there is another area, I know it's bigger here, it's generally in that direction. Let's take very small area. This one is in that direction, that one is in that direction. And you will find, like, you go away and the area gets bigger and bigger, but the r squared is going to be bigger as well. So the solid angle of this is, for this r squared, the same as solid angle of that. But this has that direction, this has that direction, and in the integration, both will cancel. So the flux of this, which is outside, through this closed area is going to be 0. In the easy way, they say to the students, the number of lines that go in is equal to the number of lines that go out. That's what they say, just to make it simple. Okay, and so the flux of anyone in the outside is equal to 0. But at the end, it comes from there. So you're only left with the enclosed charges. And here, it's the time to define or to mention Gauss's law, which was derived that way, and say that Gauss's law says, Gauss's law. Yeah. Oh, okay. No problem.
Thank you for telling me.
No problem. Gauss's law says that the integration for a closed area for the flux through every single area, like in that area, the whole closed area, is the total Q enclosed over epsilon naught. If you have space in there, if you have like other materials, then it's going to be like, let's say you have insulator inside, it's going to be epsilon, but Q is the Q free. But generally, this is right if you take all the Q's, the free and not free. What is not free is something else, another thing. But that's why you want to know. Q enclosed over epsilon naught. I just keep talking. I mentioned everything of mine. I can't be silent. Okay, so that's the Gauss's law. And we want just to apply it. It's all the time correct. It's all the time correct. But sometimes we can use it to find E. for cases of symmetry. Let's see an example. For example, if you want to find, if you have a sphere that's a sphere of radius r, and let's say it has rho inside. And this is the surface, and it has rho, constant rho, and find the electric field, for example, at this point in here. Let's say that. This is R, and this is L. Find the electric field at this point. That's what you're required to do. If you want to find it using the normal ways, then you take an integration. You have triple integrations because it's a volume. This is not going to be required, but I'm going to just show you how difficult it's going to be. The integration is going to be over r and theta and phi for spherical coordinates, and 0 to pi and 0 to 2 pi, r squared sine theta dr d theta d phi. This is not required again. That's dv for the spherical coordinates, and each one multiplied by rho. This is dq inside this, every dq inside the sphere, every point charge. And then multiply by k and divide by r squared. Let me call it s squared. It's not the same as this r. And it will have a direction as well. What is s? How far away each one is from that point. How far away it is. So this is the L, and this is, for example, r. It's not 90 degrees. It's not easy to find how far away. You want to just go to the coordinates and describe it. It's not an easy thing. So you want to know the xyz coordinates for this, the xyz coordinates for that, and then square under the square root, or without under the square root, because you need the s squared, for example. Or you can describe it by, this is a vector, and r hat, that's another vector. You want to describe it also in theta and phi, and this minus that is going to be equal to this, and you square it, which is a long thing. And then you want to take the directions, multiply by something to take components. Some components will cancel, so it's a big job to do. It's a hard thing. So the easy thing is to look at the problem in a different way using Gauss's law. So if you look at the problem, you say, okay, the electric field here should be the same as here, which is L away. It's the same as here, same as here. But logic, what is the difference between this point and that point? It's the same. We are the same distance from the center of a uniform charge distribution sphere. So it should be the same everywhere on a sphere of radius L. It should be the same. So take any point, take this surface, which has a radius of L, and say, okay, the electric field on this surface is the same in magnitude at every point on that surface. This surface that has the electric field on each point of it to be with the same magnitude is called Gaussian surface. So if we choose that surface, because I want to find the electric field here, so let me take a surface that includes that point. And that surface has the same electric field everywhere on it. In that case, why I'm doing that, in that case, I can look at Gauss's law and say E dot dA for that closed surface, because Gaussian surface is closed, is equal to that. E at every point on that surface is constant. I can take it outside. I'm left only with dA. And E is the same at every point, including my point of interest. So if I take it outside, I'm left with dA, which is easy. I can find E, and that's what I want to do. That's the point, to find E there. And in this case, look at the symmetry of the problem. It's spherical. And choose any point. Like this one will give you an electric field in that direction. But there's another one almost here that will give you another one in that direction. The same distance, the same dq's, because it's uniform charge distribution. And these components will cancel, leaving you with that component in r hat. Choose this point. It will give you an electric field. There's another point here. Give another one. The tangential one will cancel, and you're left with the radial part. So each point will give you, at the end, an electric field. Another one will give you such that the total is going to be in r hat. If you come to this point, it's going to be in that direction. If you come to this point, it's going to be in that direction. So by the symmetry of the problem, just by the symmetry, each point on a sphere of radius L is going to be with the same electric field in magnitude, and is going to be radial in r hat direction, only by symmetry, without making any calculations. So E and dA are in the same direction because that's the area, the Gaussian surface that I want to use to integrate over. That's the direction of it in r hat. And the electric field is also in r hat. So the dot product goes away. So this integration changes to integration over E dA, and that's it. Or dA small, whatever. But one of the properties of Gaussian surface is that the electric field at every point on it is the same, so I can't take this out. So it's just E dA. So this hard part is now easy. And this dA is dA of this Gaussian sphere, which is 4 pi L squared, because the radius is L. So this is going to be equal to E by 4 pi L squared. But this is equal to Q enclosed over epsilon naught. Divide both sides by that area, and then you get E. So in this case, E is going to be equal to Q enclosed over 4 pi epsilon naught R, or I'm sorry, L squared. Again, by the symmetry of the problem, E is radial outwards. So it's going to be in R hat direction. So that's the electric field in our case. For spherical symmetry, that's going to be our one, like over L squared or something. Except if we are inside to something else. Yeah.
If you are given rho, and then you make your Gaussian surface, do you get Q just by dividing rho with the like surface area of your Gaussian
Okay,
surface?
what is Q enclosed, basically? In this case, Q enclosed is the one inside your area, which is all of that. So it's rho by the volume.
The volume of your Gaussian surface or of the actual surface?
No, this solid sphere. Q enclosed is only here. There is no Q in here. That's space. So Q enclosed is the volume of the solid sphere multiplied by rho. So that was easy to find the electric field instead of having very long, complicated integrations. That's an example. The same problem, I can also find the electric field inside the solid sphere. Let me have the solid sphere again, but I want to find the electric field inside instead. So inside it, let's say a distance r small, and it has rho, and the radius is r capital. Okay, if I want to find it inside, again, I apply the same law. By symmetry, it's a spherical symmetry. This point is the same as that point, the same as that point, and so on. On a sphere, it's symmetric. And each point, suppose this point will give an electric field. There's another one that will give an electric field, the same magnitude, and the tangential components will cancel. You have radial components only. Again, you apply the same law, and E dot A, because it's in the same direction, is equal to E by 4 pi R squared in that case. Because that's the Gaussian surface. The surface that includes your point of interest and has the same magnitude of the electric field. That's the Gaussian surface, and closed as well, closed surface. So E by 4 pi R squared is Q enclosed over epsilon naught, and then E is going to be this. Yes.
Why does the Q enclose the volume times rho times dA instead of just the volume times rho?
Oh, now you're asking about the new Q enclosed, right?
Just the one thing you wrote right there.
Okay, now this is not going to be applied because that's Q of the whole solid sphere. And now it's going to be only this volume, which is inside your Gaussian surface, multiplied by rho. So it's 4 over 3 pi r small cube multiplied by rho. Q enclosed. That's your surface. What is inside? The enclosed inside it. But all of this is solid. So the volume inside your Gaussian surface that has a charge multiplied by rho in there is going to give you the charge inside.
And you also multiply by dA, right?
No, ds is I don't know. I didn't erase it.
That's what I was confused
Oh,
about.
sorry.
Yeah.
It was just there by mistake. Okay, in this case, there is r in here, which is a variable, depends where you are. And you have r down. And so if you cancel 4 pi with 4 pi and r cubed with r squared, being left with r, so it's going to be rho r over 3 epsilon naught r hat. That's the electric field for inside the solid sphere.
So for a Gaussian surface, you can always take EA out.
Yeah, because by the E is in the same direction as A, so I take E out.
So is there like an instance where you can't take EA out?
It's inside the integration.
No, like
The E?
no, like the A, because you integrated it and it became 4 pi r squared, right?
Yeah. So the integration of dA is A.
Yeah.
So what is A for the sphere? Is 4 pi r squared.
Yeah. So is there like a time where you can't take E?
Oh, when you cannot take
Yeah.
E out?
For A.
A is inside. You cannot take it out anyways.
Okay.
It's inside the integration. After I integrate, the result is going to be whatever. In the case of spheres, it's 4 pi r squared. But E, for the Gaussian surfaces, the Gaussian surface by definition is a surface that has the same magnitude of electric field everywhere. So I should take E out. But there is still a dot product before. So if the dot product is the same at every point, then yes. If it's not, I can have cosine theta with different values at different points. So I take only E and leave cosine theta inside. But you're not going to go to that level. All the time you'll find E is in the same direction as A, and you cancel the dot product, and the cosine theta is cosine 0 all the time, and it's 1. But generally, there's cosine theta in here. But if it's the same everywhere, it's just 1 or whatever, and you just cancel it. But the integration of dA is A. dA is not taken out of the integration, just E. Clear? Okay. Another example. So for spheres, it's a spherical surface. For a sheet, it's a wafer. We talked about it before. So normally, if you want to find the electric field using Gauss's law, you need to find the Gaussian surface, what it is. But what is the definition for the Gaussian surface? It's the surface where it's a closed surface where the electric field is constant at every point of it. That's the Gaussian surface. If you have a very big sheet, like infinite sheet with sigma, you want to find the electric field above or below. Let's find it above, for example. Then let's use Gauss's law. Before using Gauss's law, do we have symmetry? Can I make a surface where the electric field is the same everywhere and it's a closed surface? In this case, yes. Every point above the sheet, this dq will give you an electric field, and there's another one will give an electric field. The same magnitude, tangential ones will cancel, you're left with the vertical. So every point above the sheet will have an electric field upwards. So let's take the same height above the sheet. Let's say it's h above the sheet. Every point above the sheet by h is the same as any other point above the sheet by h. What is the difference? This point is the same as that, because it's an infinite sheet. And the electric field is upwards. So the Gaussian surface is just any surface above your sheet and below, and you close it. I may take this surface and another one below the sheet, the same, and I just close it from the sides. So it's a wafer at the end. It doesn't matter how the area looks like above, as long as it's horizontal with your sheet. So in this case, there is an area above. Let me just take a rectangle and another one down, and your area is passing through it. It has sigma on it. In that case, your Gaussian surface, the integration over dE to dA is Q enclosed. The integration, the E, I can take it out. While I'm integrating over my closed surface, that's my closed surface, I go through the upper surface while integrating. I'll go through the lower one. The electric field is vertical, so it's in the same direction as A, up. And the same thing down, it's in the same direction as A, down. So E dot dA is equal to EA. And then you can take E outside because E is the same at every point on that upper one or lower one. You're only left with the sides. You want to integrate over the sides. But E is vertical and the sides are horizontal in direction. So the dot product cancels on those lateral surfaces or side surfaces. So this is equal to 0 for this surface and that one and the one behind and the left one. But it's not for the upper one and lower one. So the upper one is going to give you E. So you can take E outside and you integrate over dA. Notice that I'm not saying over a closed surface because E dot, the dot product, like, let me just tell you what it is. So it's EA for the upper one plus EA for the lower one or the bottom one plus integration of the dot product is cosine the 90 degrees pi over 2 dA by E. This will give you 0. Exactly as an example, generally I have E dA cosine theta. For the upper one, cosine theta is 1. For the lower one, cosine theta is 1. For the sides, cosine theta is 0. So they cancel. And here E is out. This area, which is the above one, will give you A. And this one will give you A as well. So the integration of the closed surface is EA plus 0. So the whole is to A. I mean by A is the upper surface area or the lower, this value. But how much charge is inside? Because this is equal to Q enclosed over epsilon naught. That's what it's equal to. Q enclosed is every charge inside your closed area, but your sheet is passing through. And the area inside your closed area is actually A, area of the sheet passing through. Is that clear? Okay, so that's your sheet. Let's say that's the sheet, and that's your closed area around it. So there is A passing through your closed area, which has an area up and area down. So this area multiplied by sigma is equal to Q enclosed. Sigma A, that's epsilon pi. So this is equal to that. You cancel the A's and divide by 2 to have that E sigma over 2 epsilon naught. You know already that E is vertical n hat. Let me call it n hat. So it's n hat in that case. N hat here is upwards. N hat there is downwards. So it depends where you want to find the electric field. That's n hat. Depends where you want to find. Let's call it 1 or 2. And then E1 is that much, but E2 is that much. So you already know the direction. Of course, if you have an example, okay, this is J hat, so in J hat. What is the electric field below it? Oh, it's this much minus J hat. That's the point. So we're done with spheres, we're done with sheet. I hate the sheet because I talk a lot about it. I'm real TA for the sheet. And then let's go, yeah.
If you're looking for the flux just through the top or just through the bottom, are you still multiplying by 2, or are you not multiplying by 2 there because you just want through one phase?
Through the upper one is EA. That's it.
Okay.
But you're integrating over the closed surface. So the upper, lower, and the sides. All of them together will be enclosed over epsilon.
Okay, so the electric flux through the whole thing
Yeah.
tends to.
You can just, if you want to make it, you see, it doesn't depend on the height. So you can go back to your question and take a wafer such that the upper surface, upper area is very close to your sheet, and the lower one as well. And the sides are very, very, very small and thin. And so the flux through them is zero. Even if they all have not zero, not 90 degrees with E. They're very, very small areas. So the integration of that area is zero. If you want.
So if you had a problem to ask, like, what's the electric flux above this surface, you would not multiply by 2 because it just wants.
Tell me what the area is.
Okay.
Flux through what? Through this area or through this area? It differs. The flux will be more, depends on how much charge you have inside. But I'm finding the electric field, not how much flux is there. The more the area, the more its flux.
So the Gauss's law is an equation of flux to use to solve for E.
Yeah.
Okay.
Okay.
And that's why the sides don't matter, right? Because it has to be perpendicular.
Yeah, in this case, it didn't matter because they're perpendicular to the electric field. They give zero.
Right, and you don't care about the normal direction of it.
From direction of what?
The upwards direction from the sides or whatever. It
Yeah,
doesn't
that's the
matter.
electric field direction everywhere.
Parallel.
Yeah, it's tangential to the area, but the area is in that direction. So the dot product is zero for the sides.
Okay.
Yeah. Okay. Let's take the last example, which is for a rod, before finishing the flux and Gauss's law, and go into the energy. Maybe we'll take the energy for tomorrow. I don't know. Leave it for tomorrow because it's a new subject. And see an example that I will use almost all the things in it. Let's have a rod, and let's have. I'll make it some difficult a little bit. Let's have a cylinder. It's an infinite rod or infinite wire, and solid cylinder of radii. Of course, this is infinite as well. Of radii A and B, for example. So that is a solid cylinder. And also I will make you suffer by adding a third cylinder. just to include everything, you know? Which has only surface, like it has a very small thickness. It's just a surface because I want to have a surface charge density. Okay, so if you hear me, you know what I'm talking about. The wire is infinite. The wire is infinite and it has a uniform linear charge density of lambda. That's the wire. Has lambda on it. This solid of radius from A to B. Okay, this is A, and this is B, and this is C, and this is ocean. Just kidding. Okay, so if you have that, the wire is infinitely long and has uniform linear charge density of lambda. The solid cylinder of radii from A to B, it has a uniform volume charge density of rho. And the sheet at the end of a radius C has a uniform charge density of sigma. I don't want to go through any numbers, just to have the general equations. And you are required to find the electric field. I said Okay. I don't know, they don't talk English, the market, right? Typical language. Maybe it's the easiest. English is very easy in comparison with the other languages. Yeah.
What else do you know?
Arabic.
Well, what else? Anything else or no?
Huh?
Anything else or just Arabic?
I know some words in Spanish. I can make simple sentences in Spanish. For simple present. Okay. In here, let's find the electric field for radius r less than a, between a and b, between b and c, and more than c. And that's it for today, which will take an hour. How is the time? It's 8:14. Hopefully, like, yeah, that will take like maybe 15 minutes if no one asks any question. Let's see, maybe less. Okay, let's find E for R less than A. Okay, because we have infinite, infinite, infinite. So go R away from the rod, less than A, of course. At every point R away around should have the same electric field because they're symmetrical. And also the electric field is radial in all the directions from the axis. Because any point like this will give an electric field, and there's another point that will give another electric field, the same magnitude, and the tangential ones will cancel, or the horizontal ones will cancel. So I'm expecting the electric field to be radial, away from the axis. And so you may ask, what about the outer ones? They will give an electric field as well. Yeah, the outer ones will give. You'll find one that will give in that direction, you'll find another one that will give in that direction. And you'll find lower ones that will give in other directions up. At the end, they're going to cancel, but they will give the same, and you can show that it's also radial. Like at the end, those uh, angular components will cancel, and you're left with radial, but you're not sure how much it is. So you know at the end it's radial, and every point this and this and that on a cylinder surface is the same because all those points are symmetrical, uh, analogous. What is the difference between this point and that point and that point? Like around, no difference. They're the same. Maybe the direction of E is different, but the magnitude is the same. So the best Gaussian surface, including your point, and which is a closed surface, having an electric field which is constant over every point of it, it should be a cylinder. So for such cases, it should be a cylinder. What I'm saying now is applied here, is applied here, is applied there. It's the same. E is going to be radial, and if you are at the same distance from the axis, the electric field is going to be with the same magnitude. By symmetry of the problem. So we take this cylinder and we try to find the flux for the whole area, which is the lateral area and these areas. But the flux for these areas is zero because E dot A is zero. E is not the same at this area and the lateral area. Even here differs from point to point. But because the flux is zero, who cares? Okay? So let's take that one with the length L and say that the integration over a closed path E dot dA is equal to Q enclosed over epsilon. Now, what is Q enclosed in that case? Inside the Gaussian surface. Who knows?
Can you repeat it?
Yeah. What is Q enclosed inside my Gaussian surface? It's only the rod inside.
Lambda.
Lambda L.
Yeah.
Okay. Lambda L is Q enclosed. So let me just get done with it. Lambda L divided by epsilon naught. So I need only to find E dot dA. E is the same everywhere and it's outward, which is the same direction as the area. The dot product goes, cosine the angle is 1 all the time. E goes out, so E by dA is equal to lambda L over epsilon naught. This is wrong right now because not the area over the closed surface where E is constant. it's not constant over the sides. So the flux through the sides is 0, but the flux through this area is the one that will be left, which is not a closed area anymore. I mean the lateral one, where E is constant over it. Same as the sheet that we did, just the upper and the lower. So this will be equal to that, and so E by the area around, which is 2 pi RL, is equal to lambda L over epsilon naught. And so E is lambda, of course, cancel L with L, doesn't depend on L. And in R hat direction, radially, cylindrically radial. I may not write anything new. I will use the same equation, just change things in there. I'm not going to write more. Is that clear? Okay. It's clear. Let's go to the second one. Now you do know all the details and symmetry and the direction and what is the Gaussian surface and the flux is 0. I don't need to repeat that. So I'll take the same thing. If you go between A and B, you are inside this solid. So I'll take between A and B instead. E dot dA is equal to what is the charge inside? So instead of having this, I will have this. So that's my surface now. Should go there. Okay, so that's my surface going through the solid between A and B. You understand it? Okay. In that case, E dot dA is equal to Q enclosed. What is inside my surface?
The same charge.
Which is lambda L?
Yeah.
That's one of them. That's inside my surface. This is correct. But there's still some of this one because I'm around here. That's the Gaussian surface. It has some parts of the solid inside it. So there's still charges from that solid cylinder inside it.
Oh, I didn't see the rho. Yeah, it's just the rho times volume.
The rho times this volume inside my Gaussian surface. Is that clear?
Yeah.
Okay, what is that volume? It's the volume of a cylinder of radius r minus the volume of a cylinder of radius a. So you will get that thing in between. The volume of a cylinder of radius r, is pi r squared multiplied by L minus the volume of a cylinder of radius a by a squared L. So this one multiplied by rho is Q enclosed from the solid cylinder. What is clear in Spanish? Claro? Claro?
It is, of course.
Oh, I don't know that. I just threw it out of my mind. Okay, so that's Q enclosed. You apply it here, you apply it there, everywhere. So this is going to be plus, take pi as a common factor, L as a common factor. L pi r squared minus a squared. All of that. And do the same thing in here. Lambda plus pi r squared minus a squared by L over epsilon naught. And then instead of that, you cancel L from both sides, and then plus pi r squared minus a squared. It's a difficult exam. It's not going to come in the exam.
Thomas.
I think I don't think it's going to come like that. I don't promise. I don't think.
Where did rho go?
The row. Oh, sorry. Row multiplied by this one here, and row in here multiplied by only that part, and multiplied by that part. Thank you. Now let's go between B and C, which is here. If we are here, just Q enclosed is going to be different. That's the thing. Let's say area is 2 pi RL. It's a new R. It's a new R. That's it. And Q enclosed is going to be just almost the same, but we change only one thing in there. Who knows what it is? Yeah.
It's the whole cylinder, not just part of it.
Yeah. So what is the thing that I want to change in here?
Replace R with B.
Yeah.
Who said that? You? He said that. Okay, so you know that. So it's the whole volume in here, as you said, and the whole volume instead of R minus A is B minus A. So we replace R up by B instead. That's B, and that's B, and that's B, and that's B, not the one down, because that's coming from the surface, the Gaussian surface. And then this is between B and C. Just replace it by B. Wherever you go farther on farther, the Q enclosed of this part is going to be the same. Now, if you want to go more than that, like you take this Gaussian surface force for R larger than C, you do the same thing. And let me just use a black one. Oh, no black. Okay. If you are at R larger than C, then E dot dA is the same. You have Q enclosed due to the wire. It's there already. Due to this solid cylinder, it's there already. You need to add another one, which is the one of the shell. So it's just sigma multiplied by the area of the shell, which is 2 pi CL. That's the area, 2 pi CL. And here the same thing, 2 pi CL by sigma, of course. And here the same thing, 2 pi CL by sigma. And here we added 2 pi C sigma because we canceled the L from that side and this side together. So it's gone. So that's the equation of force in R hat. For the last. Now we started at 17, I think. 8:17 or 8:14 when you started that. Yes, 12 minutes. I'm done, except if you have any questions, because it's better leave the energy to.
What time's tomorrow?
That's a long question. Needs integrations too. Okay, let me just stop this. Thank you for the video.